Okay, everybody, welcome to the GBO Community Zoom event. Can people hear me, Jay, or somebody give me a thumbs up? Or yep, thumbs up. Thanks.
Yeah, we can hear you. Yep.
Okay. Welcome to the Community Zoom. We're going to get going here. I see we have 38, 39 more people are showing. Oops. So I'll just quickly give you some observatory updates, some news. The EPO group is planning to having a big lunar eclipse party this Sunday evening, starting at 5:30. There is a lunar eclipse happening, and it's also going to be like a public open house event where the public is invited. It's outside to mitigate COVID, and so that's going on this weekend on site. The GBT proposal results are expected to come out by the end of next week. We're aiming for around May 20th. So people will put in GBT proposals at the early February deadline. We'll find out the results hopefully by the end of next week. Our summer students are arriving May 21st, coming up. This first time in 2 years that we are going to have our undergraduates on site. So that's exciting. And then soon in the first week of June, the first full week of June, the GBT will enter its summer maintenance season, where we basically sort of shut down and do more extensive maintenance during the day, and then we'll observe over the weekend. Sometimes we do drift scans at night. So, so that's the current upcoming plans of the observatory. I'm going to hand it over to Jay, who will introduce our speaker. I'm going to hit stop share. Okay, Jay, go ahead and take it away.
Thanks very much. Let me just say that the schedule for upcoming talks in this series is available on our website. There's been one change. Scott Ransom is moving back 2 weeks from what is apparent on the current schedule. We'll get that updated really soon. Our speaker today is Di Li from the Chinese Academy of Sciences. He's the chief scientist of FAST, the 500-meter aperture spherical radio telescope located in China. And he's going to be speaking to us today on polarization results of fast radio bursts using data from FAST and the GBT. As always, if you have questions, please submit those in the Q&A button in the lower right hand of your screen, and I'll now turn it over to Di.
Thank you, Jay. I'll put it on full screen, and so is it visible? Okay, good. So I will. So this is want to introduce a work published in March, but it's a little bit more general discussion on fast radio burst. So this whole field started in 2007 when Duncan Lorimer published his famous Lorimer burst, but it's only got its name in 2013, since in the initial years nobody believed in Dunk's sort of single burst. And this I really like this abstract of those two initial papers with forward-looking statement. So in the first paper, the author stated that hundreds of similar events could occur every day. It's quite audacious, right? At that moment, they only have one burst, and that is also not well accepted. And then in the second paper with formal detection, the statement is that it offers an opportunity to determine the baryonic content of the universe. I think both has been not only realized, but far exceed the original expectations. So by the time that Duncan made it to the FAST site, it has become a really fast-growing field. So the major landmark in this field is the discovery and localization of 121102, the first repeater, in the effort led by Xiaomi Chatterjee. It put for the first time confirmed the cosmological origin of a repeater. So then we can actually estimate the energy. So in 1,000th of a second in this sort of one single burst, showing that this is actually a real burst. It contains enough energy to say sustain human society for 1 trillion years. So well, the equivalent energy. So it's still not well explained. So in terms of the model, there's this website, FRB theory wiki, with more than 50 entries, and each entry is just a type of models like AGNs, neutron star mergers, black holes, and axions and aliens. So I think it's fair to say we haven't even reached the stage of sort of convergence. And that reminds me of this this opus of Immanuel Kant, and there's this quote from the Critique of Pure Reason. It says, human reason in one sphere of its cognition is called upon to consider questions which it cannot answer, but presented by its own nature. I think our own field, astronomy, is very good at making discoveries, but it's very hard to actually solve anything completely. I think this fast radio burst is the sort of most recent in line. So the prospect of really getting to it, understand its physical origin, I think is unclear, but it's an important subject for the coming decades. So the FAST telescope, since its first proposal in 1996, finally, after more than 2 decades, reached normal operation in 2020. But in the last 2 years, also data from FAST has facilitated more than 120 papers, including 5 on Nature, 1 on Science, and 2 on Nature Astronomy. So it has been fairly productive. And in terms of fast radio bursts, 4 new FRB have been published, also from our drift scan blind survey. So they are here. So in terms of number, it's really not competitive, say, compared to CHIME, which are those yellow dots. In one paper last year, CHIME published 500 sources. So that really is a game changer in terms of the sample size. However, the fast detection does occupy this larger dispersion measure, presumably more distant and dimmer burst. So, so that still provide us insight into the more higher redshifted population. So based on, since this is a blind survey, it's a uniform survey. So based on this 4 detection in 1600 hours, we can estimate an event rate of fast radio bursts. It's sort of the lower limit event rate at 120,000 per day per full sky. And if even weaker bursts exist, and we have no physical reason to believe that it will not. So in the era of square kilometer array, we'll be looking at somewhere between 1 million to 10 million fast radio burst event per day. So this really, we're looking at a very dynamic sky. So we in the August of 2019, we are testing our transient backend. And at the end of the testing, at the end of August 2019, we start to catch a very bright burst from 1211.2, the first known repeater. So we put it on ATEL, and then it also motivated the subsequent monitoring campaign. We basically look at the source 1 to 2 hours every day until it finally turn off in August. So in the time span of little less than 60 days with effective observing hours of 59.5 hours, we get 1652 bursts that in terms of brightness or equivalent energy, it cross 3 orders of magnitude and have this bimodal distribution. So the total number of bursts from this source in the previous literature is a little more than 300. And the total number of bursts from all sources in all papers, it's I think is little less than 1,000. So we can see that on the higher energy end, it goes from flat and goes steeper and steeper asymptotically, approaching a power law of -2. And lower energy end is seems like a log normal, although below a certain detection threshold, we start to lose the real constraint on the width of such distribution. So I guess the punchline is that we did get this robust characterization of its peak energy of the peak burst rate, and the lower energy end can be well described by a log normal function, which usually hint at a stochastic process. And at higher energy end, we can describe it by a sort of generalized Lorentz function. So it's basically when the E goes small, it's flat. When the E goes large, much larger than E0, it's approach alpha E, and in this case, it's consistent with alpha E being 2. And that can also be described by the ratio between 2 independently random variables, basically the area under 2 Gaussian functions. That happens in atomic emission. For example, if you have 2 random processes that have coincidentally correlation, but I think it's a progress in provide some basic characterization of repeating burst, but we are still far away from getting to its physical origin. So with such a large pulse set, we start to look into its polarization. Since 121102 is famous of having very large rotation measures. So the RM is the integral, path integral of the electron density times the magnetic field strength. And the 121102 have been measured to have RM close to 100,000. So it's one of the largest RM ever measured for astronomical sources. So out of the 1,600 pulses, we have about 300 that have really nice line profile and high signal to noise ratio. But we cannot even get a single detection of polarization. So really, it's troublesome. So at first, I thought it was channel smearing. So basically, you have if the original pulse is intrinsically, say, 100% linear polarized, but we only have a limited frequency resolution, so you can have intra-channel smearing, and that's roughly given in those formulas. So the angle rotated within the channel is roughly goes linearly with the channel width. However, we go back to, say, baseband data that we have for a limited number of hours and go to much finer channels, we still cannot get a RM measurement. So that seemed to be not the case. And for some pulsars, they have been shown to have intrinsic frequency evolution. And that has been explained by having different height of the emission site. And in that case, if it's due to the structure in magnetosphere of a pulsar, usually it happens at higher frequency rather than lower frequency. So the depolarization is more severe in high frequency. And that also is not the case, since say for 12, 11, or 2, we later realized that the RM have always been measured between 4 and 8 gigahertz. And we operate at L band, so it's 1.2 gigahertz. And then we start to look into other repeaters, and later we also have this joint campaign with GBT to look at active repeaters in both L band and higher frequency band. So it's C band, S band. And it turns out that it's always that at higher frequency band, you get higher fractional linear polarization. And it's also plausible that all the sources are intrinsically 100% linear polarized. So that brings us to the realization that that is likely due to multipath propagation. So in that scenario, the degree of depolarization is due to the addition of signals that go through different paths. So at any instant that you measure the pulse, also measure the RM, it actually contains information of, say, different electron clumps, and also may have a varied magnetic field along the path. And that has been discussed in many other contexts. So this particular reference is about the AGN environment. You can see that the depolarization effect has a very steep dependence on the frequency and this single parameter, so-called sigma RM. So the sigma RM is the sigma RM along the transmission path. It's not the sigma RM measured in one's own data set. So it could be due to a combination of the variation of electron density or changing of magnetic field. And so that's it's sort of the PR plot of this joint observational campaign. And the main result is in this one graph. So each color stands for each source, and we collect data from FAST and GBT, and also archival data from chime at lower frequency, and VLA generally at a higher frequency, and also several bands from Arecibo, VLA, and LOFAR and ASCAP. And you can see that it's a general trend that at higher frequency, the degree of polarization goes higher, and some sources did approach 100% linear polarization, and at a certain characteristic frequency will drop like a stone, then really goes to 0 at a much lower frequency. And they can all be well fitted by this curve. So that's the depolarization due to multipath propagation. And also it's worth noting that the sources, there's a sort of two blue curve fit are the two most active repeaters. So the one on the rightmost is this 2019 0520. So this new repeater discovered by FAST and monitored by GBT, and it will come out in Nature probably later this month or next month. And the second sort of to the right is 121102, and these two sources are also the only two fast radio bursts that have a confirmed compact persistent radio source. So I think this is not coincidental. So we do look at a scenario that the younger burst have a more complex environment. So basically it will have more electrons around the source, and it's in a more varied environment. That also gives rise to the persistent radio source, but it will evolve rather quickly. It starts to clear out its environment, and its activity level will drop and go into a mode that was a simpler RM, or even a lower percentage intrinsic polarization. So that's basically our paper. And a accompanying modeling paper has also been published on APJ. So that's led by faculty in Yunnan University, Yuan Pei Yang. So we basically have this descriptive, relatively simple multipass parameterized multipass scattering model. So we have this scattering screen at a certain distance to the source, and it has a size scale of the clump of electron density, and it also have a turbulence spectrum to describe its variation. And by varying this combination of parameters, it can produce the sigma Rm, and we can also fit the changing of the Rm with this this parameterized sigma Rm measurement. The bottom line is that there will be many combination of parameters that can fit the data, but the current favorite is that if you have an electron screen about 1 parsec to the source, and the source is a magnetar, basically a strongly magnetized compact object, then the density in the electron screen will be about 1,000. So that's relatively high, but not impossible. And the magnetic field in the electron screen is about roughly about 1 milligauss. And a nice prediction of that model is that if you have this screen with this structural function, basically this power spectrum of density, it will also predict that the sources with higher sigma Rm will also have larger scattering time width. So basically, you have more signals that can combine and arrive at in the observer's frame at one instant. And we do see that correlation in the 6 sources in our paper. So in that paper, there's basically this 2 apparent relation. One is the source with larger sigma Rm has larger scattering time. And another one is that source with larger sigma Rm also have larger absolute value of the Rm measurement. So I think both are consistent with this simple picture. So I think this is potentially a unified description of active repeaters, which seem to all reside in this complex plasma environment. It has some sort of magnetized source, probably a compact star at the center, and we still cannot say exactly what it is. It may be magnetar, it may be a black hole environment. And we have some recent work. There are 2 papers on AstroPH that also showing for 190520, this FAST discovered new repeater. There's on month-to-month time scale, you can see even sign changes and it's of the RM. It goes from say negative 10,000 to plus 10,000. So that cannot be explained by change of electron density alone. So that probably have to be a sign change of the line of sight magnetic field. But that's so I think that is still being analyzed and also being reviewed. So to round off the talk, I have this short video. So hopefully it's not too noisy. So it shows the almost the real fast sky with the burst. The rainbow is supposed to be the dispersion measure. And it seems that the origin of the fast radio burst, at least for the repeaters, is coming out of this like some type of explosive event that ionizes the environment. Right. So I have another quote from Kant. So in his book, he does concern about some fundamental questions. So I think the primary question for the philosopher is the existence of God, but in this particular instance, it also applies to the general question we are facing, since we still know very little about the origin of FRBs. And it divides the knowledge into definitional truths and a priori knowledge. And then through investigation and thinking, we try to form a so-called synthetic posterior judgment. And for a type of phenomenon that really are still at a very initial stage of experimental characterization, I think the challenge is to ask the right questions. For example, I think these roughly from 2 years ago, we have in 2020, we have this FRB symposium, and there's an online poll asked the question that whether one believe all FRB repeat, and the outcome is roughly 50-50. So we still cannot, within the field, cannot converge on such a very basic question. I think even by now, I think it's still an open question. So there's this interesting quote there. For if the question is absurd in itself and demands unnecessary answers, it will thus presenting the ridiculous side of one person milking a billy goat while the other holds a sieve underneath. So we do try to match the level and depth of the answer to the data that we can take. We have an upcoming proposal deadline for FAST, and this one does open to the international PIs, and you can find information on the website, or you can also inquire the observatory. So it ends on 4 p.m. UT on 15th of May. So it's only a few days away, but if you have any technical questions, you can also just shoot me an email. So this my last slide. So through a blind drift scan survey, we have set a lower limit to the FRB event rate at more than 100,000 per day. And through monitoring of 12-11-02, we have detected more than 1,600 pulses, and for the first time can characterize its highest burst rate at a certain energy. And through combining data from different frequencies, i.e. higher frequency data from GBT and L-band data from FAST, we can characterize the depolarization behavior with a single parameter, aka the sigma RM. So thank you.
Thanks very much, Dee, for a really interesting presentation. We have time for a few questions. Please submit questions in the Q&A box on the lower right of the screen. And we've got one already. What is the likelihood of an FRB detection through a gravitational lensing event? And what characteristic would identify its origin?
Yes, I think that's, I think it's possible. And actually, there have been several publications on that. I'm no expert, but my understanding is that the time delay between the events will be months, so, or say weeks. So that makes it very hard if it's a single burst event. Say, because when the burst rate dropped to a certain level, we basically practically will only get one burst rate. For example, if a source has evolved to the stage that it has one burst every year, that will be quite active in at astronomical sort of time scale, but in real surveys, it will be considered a single burst. However, it will become quite obvious with a persistently active repeater. Like basically, if you start to match one burst, then it will always happen at the same cadence. So I think with the larger and larger sort of burst set from major telescope, particularly FAST. So we have there will be several papers soon submitted on this source 2020 1124A. So that in a few months, FAST did detect like 4,000 bursts, and also we'll keep monitoring this precious few very active repeaters. I think there may be a chance to detect a lensing event eventually, because now this active repeater are still fairly close, so the probability of it going through a gravitational lens is small, but eventually.
Yeah, okay. And I had a question that I didn't understand one feature of your basic model. Is this plasma cloud created at the creation of a fast radio burst object or throughout its lifetime?
So we don't know that for sure, since we basically only see this a depolarization effect. So in the model, we only parameterize the magnetic field strength, electron density, the structural function of the electron density, and if we think the central source has the field strength of a magnetar, then we can use a dipole models to put it at, say, one parsec away from the source. So in this model, it does seem to be this electron skewing is created by the source, because it's fairly compact to the source. It's close, and also it's still varying. So it seems to be related to the source. So I also have this in parentheses, this related paper from Stella Ocker and Jim Cordes. So they analyze this new repeater FRB 190520. So in their scattering model, they compare two scenarios. One is the scattering screen is close to the source. Another one is that suppose you have a pulse source in the background, and there's a screen just happen to be somewhere in the middle of the line of sight. By the way, this source has a redshift of 0.24. However, in the second scenario, because the distance between the scattering screen and the source is much larger, it will have this sort of leverage effect. The predicted scattering width will be measured in seconds, say 10 seconds. But the measured scattering time is only a few milliseconds. So that's a circumstantial evidence that the scattering does happen closer to the source.
Okay, thank you. That's all the time we have for today. And I'd like to thank Dee Lee very much for giving us this presentation. I'd like to remind everyone that it has been recorded, and so will be available for your viewing and the viewing by your colleagues on the GBO website. Please join us again in 2 weeks when we'll have a presentation by Kim Emig on expanding views of the recombination line universe. Thanks very much, and bye.
Bye-bye. Thank you.